Yes. Thank you, the organizers, for this opportunity to present our work on this forum. So let me begin. I will be talking about our work on local structural defects and non-ergodic ground states in Martensites and Antiperovskites. Before I start my lecture, let me introduce to all of you where we come from. We are located on this west coast of India, which in the smallest state of the Indian Union, which is known for its tourism. In this state, the university is on Taligaon Plateau, with the main campus spread over 1.6 million square meters. And there are 2,000 students on this main campus and a total of about 35 to 40,000 students in the university, including all its campus spread over the state. The school building is right now at the right at the center of the campus, and in this school we have 3 master's programs in electronics, mathematics, and physics, and of course also the doctoral programs and some skill development programs as well. The main thrust areas of physics over the years has been condensed matter physics and material science, and my colleagues and I have been working on different kinds of materials and condensed matter phenomena. Recently, we are also expanding into high energy physics, and we are now collaborators in the electron ion collider. And very soon we hope to have computational physics and biophysics as well as thrust areas. So let me come back to my lecture. And before I start, let me acknowledge my students and collaborators, as well as the funders of this and facilitators, the synchrotrons, different synchrotron sources, which have given us beam time and so on for these experiments. So let me begin. I'm going to talk about Martensites and Antiperovskites, and these materials belong to a general class of materials called as ferroic materials. And as you know, in the case of ferroic transitions, there are 2 properties which are very common or most important. One is the high value of the response function below the transition temperature, and second one is the hysteretic behavior of that order parameter. And these 2 properties, they form the basis of variety of devices or applications that these materials find themselves into. And we can combine, or these two of the ferroic effects can also occur together, can couple together, and then we have multiferroic materials, which are in news today for a lot many different types of effects. This is the pyramid which connects different types of ferroic effects, the order parameters and the thermodynamic variables. And when these effects are also coupled along or happen along with the structural phase transition, we have a first order ferroic transition. And these materials have been also find themselves in large variety of applications, like for example, in the ferroic cooling, magnetic shape memory effect, superelasticity, etc. Now, what we do is we try to modulate these properties by doping. And when we dope these materials, we also introduce point defects. And as we know that, suppose I take a melt to crystalline phase transition, then if I introduce defects in this transition, then I will be able to slow down the dynamics of this transition and eventually come to a glassy state. And glass is basically a state with a short range order, or we can say that the long range order, atomic order, which is there in a crystal, is interrupted. And similarly, you can dope defects and interrupt the long range magnetic order or the order of electrical dipoles, for example, and create corresponding glassy states. So that brings us to the objectives of our presentation. That is, one of the objectives is to arrest the long-range ordering of the magnetization or strain, that is the order parameter, by adding defects. And the next objective is to identify and characterize these defects for their structure so as to know how these defects play a role in arresting this transition. And the motivation for this work came from the work of Xiaobing Ren at NIMS, wherein, for example, they took nickel titanium, which is a well-known martensite, nickel 50, titanium 50, and they doped it with different impurities. And almost every time, above a critical concentration of this doping of impurity, the martensitic behavior changed to strain glass behavior. And so the two things that we noticed was that the concentration of defects was very small, and it was almost that the strain glass state was an universal state of when you dope a martensite with defects. So our attention, we focus on this talk, during this talk, on two examples in strain glass martensites, which I will cover during the first half of this presentation. First one is the nickel 50, titanium 50, wherein we have doped nickel for titanium. And the second example I would take is iron-doped nickel manganese indium Heusler alloy, which is also a martensitic alloy, a magnetic shape memory alloy. And we will see if we can also produce strain glass in these systems. The next half of my talk will be devoted to discussing our work on manganese-based antiperovskites, which are of the ACMN3. They are perovskite structures, but only the arrangement is inverted. And we will talk about the antiferromagnetism that these materials exhibit in a cubic symmetry, and the role of this A-type atom, A-site atom, in doing all this. Let me start with a strain glass transition in martensites. So what is a strain glass? Could be the first question that would come in everybody's mind. Strain glass is a frozen, disordered ferroelastic state with a short range strain order. So it is a glassy state. So it should behave like, it should have properties of glass. So if you plot, for example, the storage modulus as a function of frequency, if you measure storage modulus and plot it, then you will see that there is a frequency dependence to this characteristic feature, which is identified as the transition temperature. And this transition temperature will follow the Vogel-Fulcher relation. That is one characteristic. The second characteristic is that the field cooled and zero field cooled curves, strain curves, will show bifurcation, and there will be an invariance of the crystal structure across the transition. That means if I record a differential scanning calorimetry, then the typical exothermic, endothermic peaks or features will not be seen. Instead, you will see just a straight unfeatured line. So so what was the picture that was available from all these studies of Xiaobing Ren? They did a lot of work on these materials, is that these materials should consist of some domains. They call them as nano domains. They could be larger also. These domains should have martensitic structure within them, martensitic order within them, but these domains are separated, such domains are separated by some defect phase. And below a characteristic glass transition temperature, the ordering of the strain vector within this domain freezes. So that is what was called as the strain glass. So we wanted to see or understand what is this defect phase and how does that small amount of defect phase cause this transition. So this is the phase diagram that is available in literature for nickel-doped nickel titanium. So you have, initially you have the long-range order or the martensitic state here. The structure is B19 prime, monoclinic structure. And above a critical concentration, which is lies between 1 to 2% of nickel, you go to a short-range order or a glassy state. We prepared these alloys, nickel 50, titanium 50, nickel 52, titanium 48, and so on. And we looked at their structure. The structure of stoichiometric alloy was essentially B2. Okay, and there was a small phase of B19 prime in this because the transition temperature or martensitic transition is very close to room temperature. But when we look at the structure of the non-stoichiometric alloys, it is B2, but the width of the peak anomalously increases, and eventually another impurity phase emerges, which was identified to be face-centered nickel phase, nickel metal phase. So we looked at the DSC and resistivity, and in nickel 50, titanium 50, we could see the first order transition or the martensitic transition very clearly, and that was absent in all the non-stoichiometric alloys. If I look at the elastic modulus, the frequency dependence of elastic modulus, then we can see the martensitic transition in the stoichiometric alloy, whereas you can see the frequency dependence of the TG in the non-stoichiometric alloy, and it follows Vogel-Fulcher relation. So what we could say is that we were successful in converting the martensitic transition in nickel 50, titanium 50 to a strain glass phase in nickel 52, titanium 48. Now we wanted, as I said, we want to understand the defect phase. So, and from XRD did not provide much information. So we thought we should do EXAFS. We recorded EXAFS, and these experiments were done at Electra. And when we do EXAFS and we extract the EXAFS signal, we want to fit it to this equation with a structural model. So what we know from the previous studies is that the strain glass phase consists of domains which have martensitic order. So we thought B19 prime, or the structure of the martensitic state of nickel titanium, could be a good model to start with to fit the EXAFS data. So we started with that, and we could fit the titanium KH without any problem in all the alloys. But when fitting nickel KH, except for stoichiometric alloy, we had some problems. In fact, we could not fit the data. There were either unphysical parameters or something. So we thought we should fit the two AGs together to minimize the dependency of parameters and control everything. So we did that. We could get a reasonably good fit, all right, but you can see here the parameters that we got, especially the bond distances, were far off from what was expected of B19 prime. And we did not have any explanation for these numbers, which were very different from what we were supposed to get. So we thought we should go back to the drawing board. And what we did was we used FEF 8.4 to calculate titanium KH EXAFS in all the alloy for all the known phases of nickel titanium. So there are three phases which are known: the for stoichiometric nickel titanium, the B19 prime phase, the B2 phase, which is the austenitic structure, and the R phase. And you can see we compared this with the experimental data that we had from our EXAFS studies. And you can see that the experimental data more or less resembles the B19 prime structure. So, okay, our first guess that the structure could be B19 prime or a variation of B19 prime was correct. And so we thought, okay, we should do the same exercise for nickel. And when we did that for nickel, you can see that the nickel experimental data, especially above 7 angstrom inverse, does not replicate the EXAFS of B19 prime, or the oscillations in B19 prime. And then we thought probably this is because when we take a non-stoichiometric alloy, we create nickel-nickel nearest neighbor pairs, and therefore we should try and see if these oscillations are replicated by nickel-nickel correlation. So we took the metastable structure of the body-centered cubic structure of nickel, and we calculated EXAFS for that, and you can see that there is some sort of a resemblance with the BCC phase of nickel. And this could be because if I plot the amplitudes, the K-space amplitudes of nickel scattering and nickel titanium scattering, then you can see that the maxima of this amplitude is at about 7 angstrom inverse in the case of titanium, whereas when you replace titanium with nickel, the maxima of the amplitude moves higher to about 8 angstrom inverse. And at higher values of K, it is the nickel scattering that gets dominated. So probably this is the reason for this behavior. So we thought, okay, in nickel 60 titanium 40, we have a face-centered cubic phase of nickel, structural phase, which we can see from XRD. So the same story should happen also in this alloy. And we can see that there is quite a good match between the phase FCC nickel EXAFS oscillations and the oscillations in the nickel 60 titanium 40, especially at the 8 angstrom inverse and above. So we thought, okay, now we have a model, and we fitted EXAFS, titanium EXAFS, with the structural correlations from B19 prime, and nickel EXAFS with correlations from B19 prime plus body-centered nickel. And we could get very good fit here. This is for the titanium age, and the parameters matched very well with the expected values. And for nickel also, we could do the same thing, and we could get a very good fitting as well as good parameters, except for we had to introduce this nickel-nickel correlation at about 2.48 angstrom, which is coming from the body-centered cubic phase. So that what it means is, if I can make a schematic of this nickel titanium doped with nickel, then you have this B19 prime structure of nickel, and within this B19 prime structure, because you have doped excess nickel, you start getting these kind of body-centered cubic nickel defect. And this defect forces a B2-like symmetry, because it is body-centered cubic, and that produces a strain. So what we said was, doping nickel in nickel titanium will produce nickel-nickel nearest neighbor pairs, and that will form body-centered clusters of nickel, which will force B2-like symmetry within the B19 prime phase of nickel 50 titanium 50. With increasing nickel concentration, the titanium local structure we found to remain unchanged. So we can say that the parent nickel titanium, or the nano domains, or those structural domains of nickel titanium are unaffected. But as there are these defects of initially which are body-centered cubic in this, and eventually with increased nickel concentration, there is a structural change of this defect symmetry from body-centered cubic to face-centered cubic. And this is the reason why we have interruption of the long-range order. This defect causes the interruption. So we said that strain glass transition is caused by composition fluctuation due to impurity doping. And the structure of the defect phase is nearly compatible with the structure of the main phase. And that is also seen here. You have almost about 2% difference in the nickel-nickel bond length in the B19 prime phase, which is 2.884, whereas in the body-centered cubic phase, it is about 2.82 or 2.84. So that is the, we thought was the reason for the strain glass phase in nickel titanium. Now we wanted to extend this to the nickel manganese shape memory alloys, which are Heusler in nature, and they have been in literature, they have been investigated by many groups because of lots of applications and different phenomena that they exhibit. And we wanted to see if we can get a transition from martensite to strain glass, and we thought we should concentrate on one of the system, that is nickel manganese indium. And there is a critical concentration, so we wanted to be a little bit far away from this critical concentration, and we wanted one impurity which would most definitely suppress the martensitic transition. So in literature, iron or Fe, when doped in any of these, generally most of these alloys, any of these systems, it suppresses martensitic transition temperature, and this is a well-known fact. So we thought we should try iron doping in nickel manganese indium, and for that we chose nickel to manganese 1.5 indium 0.5, which, because it has got a transition temperature of 425 Kelvin, which is quite high. It has, its martensitic structure is well known, 7M modulated monoclinic structure, and it has an antiferromagnetic ground state. So all these properties can be seen here in these 3 view graphs. And we thought we will dope iron at 2 places, or we'll have 2 series of alloys. One in which Fe is doped for manganese. So we create Ni2Mn 1.5 minus X, FeX, indium 0.5. And in other case where Fe is doped for nickel. So you have 2 minus Y and Fey. So we will call these as MnFe and NiFe. And I will, in the next few slides, I will compare these 2 systems as we go along. So this is the differential scanning calorimetry studies. So you can see now we introduce Fe, and as we introduce at around X is equal to 0.1, the martensitic transition appears to have disappeared. At least in DSC, you don't see very sharp transition, you see very broad phase. In the other case also, you see a suppression of martensitic transition and some very funny looking differential scanning calorimetry graph here. So in both cases, the martensitic transition has eventually disappeared. So we looked at the structure, and I told you the structure of the strain glass phase should remain invariant. That means it should be austenitic structure, in which is the Heusler structure, L21 structure. But we were in for a surprise. In the case of Fe point MnFe, okay, the structure still remains martensitic or 7M modulated structure. But in the case of nickel Fe, we see cubic structure. Okay. Then we thought, okay, now we should do the elastic properties and come check whether there is a strain glass phase or not. And the surprise continued. In the case of MnFe, we see a frequency dependence of elastic properties and a Vogel-Fulcher dependence, and also bifurcation of field-cooled and zero field-cooled strain. Whereas, and therefore we called this as unusual strain glass because the structure was still martensitic. Okay. Whereas in the case of nickel Fe, we don't see frequency dependence, although the structure is cubic, which is what you expect for a strain glass, the invariance of structure across transition, but there is no property. So the question is, now you have a strain glass in MnFe, you don't have a strain glass in nickel Fe. So what is happening? How do we understand this? So we looked at magnetization measurements on these alloys, and I'm showing you only 2 examples from both the series. This is 0.75 and 0.1 in the MnFe case, and you can see the martensitic transition that is disappearing, and that is the temperature-wise decreasing. And the second thing that you see is this magnetization going towards negative, or there is a sort of a magnetically compensated state happening here, and then there is a reversal of magnetization. Whereas in the case of nickel Fe, you can see that the antiferromagnetic ground state has changed to a ferromagnetic ground state with a TC of around 330 or 340 Kelvin. So what has happened in MnFe is that there is a magnetic compensation, and in nickel Fe, there is ferromagnetic order. Now we know from literature that whenever magnetic compensation occurs, there has to be another phase which is also magnetic that will polarize the spin of your main phase opposite to the direction of the applied field, and therefore you have this apparent negative magnetization. We also looked at resistivity, and in the case of MnFe, this was typically what you expect in the case of a strained glass material, whereas here this was a typical metallic behavior of a ferromagnet, and we could also see the ferromagnetic transition here. So we looked at the structure more carefully because we wanted to understand the structure. So we went to the Indian beamline at Photon Factory, BL18B, and we looked at XRD as a function of temperature. So at room temperature, as I had shown you, the structure was modulated martensite, but at higher temperature, it becomes cubic. So therefore, we can confirm that it is definitely a martensitic transition, which is going from cubic to 7M modulated state. And we could also identify a small extra peak in this, which grew in concentration with increase in Fe content. So this is Fe 0.1, this is Fe 0.2, and you can see that this phase is growing. So what we can say is that in MnFe series, there is a defect phase, which we could identify as a face-centered cubic phase with a lattice constant of about 3.62 angstrom. That is segregating and increases in percentage with increase in Fe content. In the case of nickel Fe, which was cubic in the lab, we could identify a small impurity monoclinic phase, I2 bar M, and which disappeared also at 500 Kelvin. So therefore, there was a small martensitic impurity phase which disappeared in at a high temperature. So then we did EXAFS. We did EXAFS at manganese age and nickel age, and these could be fitted exactly as in the case of the parent material. Everything was perfectly fine. This alloy was antiferromagnetic, so this Mn distance, which is a characteristic ferromagnetic distance, was much higher, whereas in this case it was at 4.2 angstrom, which is as expected. Then we looked at EXAFS at iron KH. All these experiments were done at Petra P65 beamline, and we looked at the iron KH, and iron is supposed to replace manganese. So if it's supposed to replace manganese, then you should see an manganese indium or iron indium bond distance at about 2.86 angstrom. There was no iron indium bond distance. We could not fit that. So it was, so what we instead we got iron nickel and iron here at these distances, which are characteristic of a face-centered cubic lattice. These distances, if you take the ratio, they're exactly face-centered cubic. So the FCC phase that we saw in synchrotron XRD, we could say that that is coming from a gamma Fe nickel phase. In the second case, nickel Fe, iron is replacing nickel. So we should see a distance at around 2.5, 2.6 angstrom of nickel indium, but we could see only a iron indium distance at 3.1 angstrom. We could not see. So that this is similar to what we see in the case of manganese. So what we could say is that in the MnFe series, though Fe is doped for manganese, it doesn't replace manganese, but it segregates into an impurity phase, which is the gamma iron nickel phase. The major phase retains the Heusler structure, and this impurity phase is responsible for interruption of the long-range ordering of the elastic strain vector and the strain glass phase. Whereas in the case of iron nickel iron alloys, though we Fe should replace nickel, it replaces a manganese at the Y or Z site of the Heusler lattice, and that forces manganese to come to the nickel site. So thereby creates an A2 type disorder or an anti-site disorder. And if A2 type anti-site disorder is created, then it should affect the intensity of the 200 superlattice reflection. And it indeed, as you can see, in the case of MnFe, there is this 111 and 200 peak, whereas in the case of nickel Fe, the 200 peak disappears, signifying that there is a anti-site disorder. So what we can say at the end of this first half is that the suppression of martensite due to addition of Fe can occur can induce a strain glassy phase if there is a segregation of an impurity phase, or if Fe promotes anti-site disorder, that means iron is accommodated within the Heusler lattice, and there is an anti-site disorder, then it will give rise to a ferromagnetic ground state. So it is not necessary that every time you dope an impurity, you should get a strain glass phase. So I think I will stop here at the first half, and we can continue. If there are questions, I will answer.
Thank you. So now the lecture is open for the questions. If you have a question, please mic on.
Hi, this is Hitoshi. May I have a short question?
Yes, please.
In the nickel titanium alloy, why
Yes.
nickel can take a BCC structure rather than FCC?
What we said is that initially what we got nickel distance was about 2.4 angstroms, 2.48 angstrom, which is closer to the metastable BCC nickel phase. So when nickel concentration is very low, the third nearest neighbor is titanium. If you look at the nickel titanium B2 structure, it is almost alternating. First neighbor for nickel is titanium, second neighbor is nickel, third neighbor is titanium. So when the nickel concentration is low, it is only the first two neighbors that are nickel. So you have replaced titanium with nickel. So the first nearest neighbor is nickel. Next nearest neighbor is anyway nickel. So it forms a B2 type order, which is within the B19 prime lattice. But when you increase nickel concentration, then the third neighbor also becomes nickel and it transforms to FCC. So initially it is BCC and then it transforms to FCC as the concentration increases.
Okay, thanks.
Yeah.
So any other questions? So can I have one short question about
Yes.
this slide?
Yeah.
So I'm a little confusing because you say the nickel to mangan 1.5 minus X FeX. In
Yes.
this case, you try to replace mangan with an iron. However,
Yes.
iron is not there.
Yes.
On the other hand, if we try to replace nickel with iron,
Yes.
in this case, iron goes to the mangan.
Mangasite. Yes. Yes, it is something that we are also investigating further, because this is what we, as of today, we don't understand. When will Fe go to in the Heusler structure, and when will it segregate into impurity? So this is a topic of investigation that we are still carrying on. But if in the literature, there are many reports where Fe suppresses martensitic transition and produces a ferromagnetic alloy. So that seems to be correct. But this strain glass phase is something that we found new, and we have to investigate what are the conditions when we do have a strain glass. So we yes, that is something that has to be investigated further. We are looking into it.
Yeah, very interesting. Very interesting.
So the main point was that it is not a universal state when you dope impurities. It can be as one of the state. There are other possibilities also.
Okay, thank you. So another question? No more? Okay, please continue. Okay,
thank you. So now we move on to the next example that I want to discuss, which is the antiferromagnetism in the cubic antiperovskites. We all know what are perovskites. So perovskite is ABX3 structure, and generally A and B side are metals and X is a non-metal. I can take many examples, SRTiO3 or anything. Okay, but suppose we consider that this role is reversed. The non-metal ions sit at the A and the B side, and the X side is occupied by metal. For example, here, sodium 3O chlorine. Okay, so this is an antiperovskite. Now, what we are talking about is something known as the metallic antiperovskites, wherein the A site is an element from the main group like gallium, tin, copper, or zinc, and the B site is a non-metal like carbon or nitrogen, and X site is a transition metal like manganese or nickel or something. And a famous example is this MgCni3, which was found to be superconducting at around 8 Kelvin. So this is the structure of the perovskite or inverted perovskite or antiperovskite. And so now if I say manganese in our case, then the manganese is sitting at this face-centered position. So obviously manganese will be in this triangular lattice. So, and we know that in a triangular lattice, we cannot have long-range antiferromagnetic order because it always leads to frustration. Yes. So therefore, we thought, how are these materials classified as antiferromagnets? Because literature showed that, say, for example, if I take manganese-3 gallium carbon, it had a antiferromagnetic ground state with a Tn of about 175 Kelvin, and neutron diffraction identified the propagation vector to be half. If I take manganese-3 tin carbon, it had also got an antiferromagnetic ground state with a 280 Kelvin, and I will talk about this. This is from our own work that we identified both the orders, and it has a antiferromagnetic propagation vector along half 0. So how is this happening despite the fact that the symmetry is cubic? The lattice symmetry is cubic, and but the ground state is classified as antiferromagnetic. And if I change this Sn to indium, then there is no antiferromagnetic order. So what we thought was, two questions that we wanted to answer were origin of antiferromagnetic order in manganese-based antiperovskites. What is the origin? And what is the role of the magnetostructural transformation? Because this transition, which is indicated in red here, is a first order transition. There is also a structure change, but the structure is a cubic phase transition. Only the volume expansion happens. So how does this, within the cubic symmetry, there is an antiferromagnetic ground state. So here is the some characterization results of on manganese-3 gallium carbon. This is the XRD. It is cubic with space group PM3M. Then you can see the magnetization data. There is a paramagnetic to ferromagnetic transition at around 240 Kelvin, and then it drops to antiferromagnet at around 175 Kelvin. At this transition, you can see that the unit cell volume, which decreases, suddenly shows an increase, and then the lower antiferromagnetic state has a higher volume than the ferromagnetic state at this temperature. And the same behavior can also be seen in resistivity, which shows the hysteresis behavior and the first order transition. We also measured the entropy, and the entropy of this material shows a plateau-like structure, which is what those people who want to make applications out of this in ferroic cooling, they desire that this plateau-like behavior should be there. But yeah, it is at very low temperature and at very high fields. But nevertheless, this is a very good or a probable good material for application. So this was all fine. But when we looked at magnetization a little bit more closely, what we found is that above TC, the magnetization curves do not look like that of a paramagnet, but they have that curvature of a ferromagnet. Okay, and so that means there are short-range ferromagnetic correlations even above the transition temperature, the Curie temperature. Now, as I come below TC, yes, it is a ferromagnetic state, but the moment does not saturate. So it keeps increasing. So, okay, even below TC, there are some antiferromagnetic correlations present. And below Tn, either whether very close to Tn or below Tn, the antiferromagnetic ground state can be converted to ferromagnetic ground state under the application of magnetic field. And in fact, it has been shown that even at 5 Kelvin, a 20 Tesla field can convert the antiferromagnetic state to a ferromagnetic state. So neutron diffraction was done on these materials by our collaborators in Germany, and they found that this field-induced transition is also a first-order transition. You can see that this is the magnetic half-half peak, which disappears when you apply a 4.8 Tesla field. So that means the antiferromagnetic state is converted to ferromagnetic state, and at the same time you can see that the nuclear peak, 332 nuclear peak, shifts to a higher angle in field, telling you that the high volume cubic state has converted to low volume cubic state. At any intermediate magnetic field, you can see that both the low volume and high volume field states are present in this case. So this was very interesting as it is before when we started this. And the reason for this is based from the DFT calculation appears to be because the two states, the ferromagnetic and antiferromagnetic states, are very close in energy, and it's so it should be possible. So although it stabilizes in antiferromagnetic ground state, there is a very close in energy space, there is a very close ferromagnetic state to it. Okay, so we did EXAFS, and these EXAFS were done at P65, and we have done both manganese and gallium. And the reason for this is very simple. If you look at the perovskite geometry, if I take, for example, manganese, the first neighbor is carbon, which is at A/2, half the lattice constant. And the second neighbor is a gallium and manganese at the same distance, that is A/√2. So it may not be possible to separate out the two things just from one edge, one EXAFS in fitting, especially if you are trying to look for local structural disorder. So we thought we should also do gallium edge, because from gallium edge, we will get gallium manganese distance, which we can use it as an input for the manganese EXAFS, and then extract the manganese distance. And what I want to point out here is this is the fitting to the gallium edge, and you can see that if I use the constraints of the cubic structure and fit the EXAFS signal, I get a perfectly good fit right up to 4 angstroms. And so that means it tells you that the gallium symmetry or the correlations around gallium are in accordance with the structure. But when I look at the manganese edge, at room temperature, I do get a good fit, again up to 4 angstrom. But below room temperature, as I go below, I see this feature which is not accounted for. And this feature actually grows in intensity as I go below room temperature. So we wanted to understand this feature. So we thought this could be because there could be a distortion. We tried different things in fitting, and we thought, okay, there should be a distortion of the manganese local structure. And so we conceived a model wherein the manganese octahedra is slightly distorted within the cubic cage of the antiperovskite lattice. And we built a model based on this, and we fitted the data, and that data fitted perfectly. And what we got was the variations of the different near neighbor distance. So this is the first nearest neighbor, manganese carbon, across the transition, and not much change in that bond distance across the transition. This is the manganese gallium, and it follows exactly what happens with the lattice. Below the transition, the manganese gallium distance increases in value as compared to above the transition, which is what happens with the lattice also. There are two manganese, this distortion of manganese sublattice created two manganese distance, short distance and the long distance. The long distance was around 3 angstroms, and that was again invariant across transition, whereas the short distance suddenly showed a decrease at the transition. transition temperature from 2.75 to about 2.70 angstroms. So what we thought by looking, we know that if there is a manganese distance which is lower than 2.75, then it almost always aids in antiferromagnetic order, whereas if there is a distance which is higher than 2.75, it gives rise to ferromagnetic order. So what we said was, in these antiperovskites at lower temperatures, the manganese sublattice is distorted. There are long and short manganese distances. The long manganese distance is responsible for ferromagnetic interaction. The short thing is responsible for the antiferromagnetic distance. And this collapse of manganese at the first order transition should have resulted in a symmetry change, which is then accommodated by the lattice by increasing itself and providing that much needed space for the manganese octahedra to distort. So with this knowledge, we tried to look at the manganese tin carbon, manganese 3 SNC, which is also cubic at room temperature, and it also shows a first order transition, same type of volume expand transition at the magnetic transition. But in this case, the magnetization, when was recorded, it was a typical of a ferro or a ferri magnet. Okay, even the paramagnetic Curie temperature was positive, so indicating that there are ferromagnetic correlation. But when and the entropy change was very high and very close to room temperature, which is good thing. But when we did room neutron diffraction, we could see both the orders, the antiferromagnetic order along the 110 direction, as I said, and the ferromagnetic order. So the manganese sublattice, there were two magnetic manganese atoms, one that carried a ferromagnetic spin and the other that carried antiferromagnetic spins. So how do we reconcile this from EXAFS? So we thought first we should understand the magnetization better, because this itself is very interesting. Within a cubic structure, you have two types of manganese atoms. So we looked at the magnetization very carefully, and I would like to point out the magnetization curve at around 280 Kelvin. And you can see, if I just isolate that curve, you can see that the magnetization initially increases and then decreases and again starts increasing. So this was just one loop, one cycle. So we completed the cycle, and what we see is, so this is at 277 Kelvin. So we followed one type of protocol. We took the sample above its Curie temperature and cooled it in zero field from above this Curie temperature to the desired temperature. So let us say in this case, it is 277 Kelvin. Then we start measuring the magnetization as a function of magnetic field. So you can see that the magnetization first increases as shown there. Then it slows a small decrease, and it keeps going right up to, let us say, 4.5 Tesla. And then when we reverse, so this is all normal, the magnetization is higher in the reversal phase than in the first cycle. In the reverse cycle, it is higher. But at some value of field, the magnetization in the reverse cycle becomes below the first cycle value, which is like a magnetization reversal is happening here. But when I bring back the field to zero and I go back again, then I don't get this crossover type of behavior, but I get the normal behavior. So, and then if I repeat the cycle again and again and again and again, I always get this red curve. I don't get the blue curve. So the blue curve comes only on the first time when I cool the sample from above its Curie temperature to the desired temperature. After that, it is always the normal magnetization behavior. So what we thought is there must be some spin dynamics. So we did time-dependent experiment. So we followed the same protocol, cooled it in zero field from above its Curie temperature to the desired temperature, and we applied a strong field of 4.5 Tesla. Then we saw how the magnetization behaves as a function of time. So initially, the magnetization decreased very sharply. Then there was some kind of a discontinuity and it started decreasing very slowly, indicating that there are two types of relaxation times. One which is a short range relaxation and one which is a fairly long relaxation. This we continued measurement for about 60 minutes or about 1 hour. At the end of 1 hour, we switched off the magnetic field. But the temperature was maintained the same, 277 Kelvin. And then after about 4 hours, we reapplied the 4.5 Tesla magnetic field, and we see that now the magnetization is almost constant. It does not have this kind of initial fluctuation. So that sort of explained why only in the first cycle we got this reversal behavior, but not in the following cycles. And it also explained that the relaxation time is of the order of few minutes at least, so that you can complete the one cycle fully. So we measured the relaxation times also, and we came to conclusion that, okay, when we apply the magnetic field, all the three spins that we saw in the neutron diffraction, all the three manganese spins align ferromagnetically, but with time, the two of those spins flip to give you an antiferromagnetic order, whereas the third one continues to remain ferromagnetic. So that is the reason why you could see the two spins in neutron diffraction and antiferromagnetic order and ferromagnetic order. So this was the interest with which we tried to understand from EXAFS. And the experiments again were done at Petra, and these were fitted. So I have two models here, what I call as a regular octahedra model, which is the cubic structure of the manganese 3 tin carbon, and it fits the tin age perfectly well without any problem, but it does not fit the manganese age at all. It shows quite a discrepancy from here. You can see that here. But if I distort the octahedra in the same way as I distort in the case of gallium compound, I get a much better fitting. And as a function of temperature, we measured the SN-Mn distance and the manganese long and short distances. And you can see that there are indeed two distances. At near the Curie temperature, the distances show a lot of change in this. So what we thought was this distorted octahedra, because of the magnetic structure, could be elongated in one direction and shrinking in the other two directions. So it is the local symmetry of both in triangle manganese octahedra is not cubic. So the triangular symmetry is not there anymore. So that facilitates the antiferromagnetic order. So it is the strain that is created by the different A-type atom, say gallium or the tin, because their sizes are different, that makes the octahedra distort differently, that gives these different properties to these antiperovskites, very simple looking antiperovskites, but it is essentially the distortion of the manganese octahedra that gives you these properties. So we tried to look at the full solid solution of manganese 3 gallium carbon and manganese 3 tin carbon. And we can see that we can dope from x is equal to 0 to x is equal to 1. And we see a very good Vegard's law dependence, and the lattice constant also increases very smoothly as we go from 0% tin to 100% tin in doping. All the compounds were cubic, and this was the variation of the transition temperatures, and this is the full width at half maximum of these diffraction peaks, for example. And as you can see that in the middle of the solid solution at the in between concentrations, the width of the peaks was much higher as compared to the two ends of the sample. We looked at magnetization, and here also we could divide straight away into three categories. These are the gallium-rich alloys, which show a behavior which is similar to Mn3GaC. These are tin-rich alloys, which show behavior similar to Mn3-tin-C. But then there are the intermediate alloys, which show very different behavior. And we tried to look at one of them in greater detail, that is the central composition, gallium 0.5, tin 0.5. So this is the gallium tin 0.5 magnetization data. And you can see that from paramagnetic state, suddenly the magnetization increases very strongly. And then suddenly it, as if there is an antiferromagnetic transition here, and then it again increases back, which is seen in all fields from 0.01 Tesla to 5 Tesla. And we were also perturbed by this broad feature here, which showed a bifurcation between field cooled, zero field cooled, and with field that bifurcation decreased. And it's as if there was some sort of a glassy transition. To look at that transition more carefully, we did AC susceptibility, and we found frequency dependence, which again was as per the Vogel-Fulcher relation. And so we could conclude that the ground state of this material is a cluster glass, but there could be a magnetic ordering. So we don't know. So we looked at neutron diffraction to identify if at all there is any long-range magnetic order. So we did this experiment at two different reactors. One is in India at Dhruva reactor in BRC, and the second one was at Berlin at E6 beamline at BER2. The reason why we repeated these experiments at BER2 was because of the wavelength. Here, the wavelength was much longer, so we could get a better Q-space resolution to identify the magnetic peaks. And in both cases, we could clearly see two magnetic peaks, one from half-half zero wave vector, which is similar to that of Mn3 tin carbon, and the other one coming from half-half-half, which is similar to that of Mn3 gallium carbon. So there are within a cubic structure, there are two magnetic orders that are being stabilized. One that is similar to that in the one end member, other one it's similar to that in the other end member. But the overall global structure is single phase cubic. The only thing is that the width of the peak was the highest as compared to the others. Now we did EXAFS, and these experiments were done at Electra, and we did at room temperature and at liquid nitrogen temperature, and we tried to fit the data with the known structure, that is the cubic model, and there were some discrepancies. We could not, this is the K-space data, so I'm showing you raw EXAFS, and we could not fit the thing, neither with the cubic model, which is using the constraints of the structure, nor with the relaxed model, so the distortions and things like that. So we thought, okay, maybe we should try something else, and we did some LCF analysis. So we tried to fit the structure with a combination of manganese 3 gallium carbon and manganese 3 tin carbon, and we got fairly good fitting for EXAFS as well as for the near edge. And the percentages that we got were also very close to what we had to start with, something like 45% of gallium and 55% of tin. So we thought, okay, we'll conceive this model now and fit the EXAFS, and we could fit it very well. So using the neutron and the EXAFS data, we could say that the ground state of this material is a cluster made of clusters. There are gallium-rich clusters and there are tin-rich clusters. And in the gallium-rich clusters, the magnetic ordering is along the half-half-half direction, whereas in the tin-rich cluster, it is along the half-half-zero direction. So the strains that the A-site atom produces, they actually hold on, creating these kind of local phase separation or local magnetic clusters, which could be identified from EXAFS. So we did for the full entire series at Photon Factory in 12C and NW10A, the gallium age, the tin age, and the manganese age. Everything was done at these two beam lines, and right through the series, we could see that there is a what you call phase separation, which can be seen here also. This I am plotting gallium bond distance as well as the tin bond distance, and both of them, these are basically lattice parameters, and both of them show a very different behavior. And this green curve here is the way the lattice constant varies across the transition. So what we can say is that the antiferromagnetic order in the manganese, these antiperovskites, is because of local structural distortion limited to the manganese sublattice. The distortions of manganese sublattice is dependent on probably the size of the A site atom. The smaller the size, greater is the distortion. And this leads to formation of gallium rich and tin rich clusters, and that the packing of such clusters within the single cubic lattice is causes some sort of a lattice strain, and this lattice strain is responsible for magnetic properties of these antiperovskites. So that brings me to the final conclusion of both the examples that I took. In the first example, we said the strain glass transition is caused by composition fluctuation, and the defect phase, the structure, local structure, is nearly compatible with the structure of the main phase. And it is strain glass state is not the only possible ground state in impurity doped martensite. It could be either a ferromagnet or it could be strain glass, at least in the Heusler alloys, and we need to understand this a little bit more. The local structural distortion of this octahedra are dependent on the size of A site atom, and the local strain that is imparted by this A site atom is responsible for the change or the different types of magnetic orders that these materials exhibit. So, and there it at the 50-50 compositions, it forms magnetic clusters with different magnetic order. So thank you very much. And I leave you with some beautiful pictures from the place where I come. Thank you.
Thank you very much, Professor Priolkar, for your nice, wonderful talk about the intermetallic system, I should say. And it is, you show the structure, property, relation, and especially local structure affect the magnetic and strain and another physical properties. So now the paper is open for questions, comments. So from the audience, so please mic on and make a discussion, please.
Yes, Chris is almost speaking.
Yes, please.
Professor, I don't have a question exactly. I have a comment. That was a very entertaining and very good talk. The slides were very clear. And actually 2 excellent detective stories where you had to put a whole load of things together to try and piece the puzzle together. Really interesting, and thank you very much.
Thank you. Thank you.
So any other comments or questions?
Yes, may I have a question?
Yes,
I'm
okay.
a bit confused,
Okay,
or I
please.
might misunderstood. The last topic you showed as the manganese 3 gallium tin carbon antiperovskite.
Yes.
And the phase is separated into manganese 3 gallium carbon and manganese 3 tin carbon, because the zones were split by 2 spectra. So,
yes.
Yeah. But the magnetic property is different from the 2 phases. So
no, no. In the magnet, I will show you the neutron diffraction data. You can see that around 155 Kelvin. This is the data at 155 Kelvin. Below 155 Kelvin, there are 2 magnetic orders. This is half of 0, which is like that of manganese 3 tin carbon. This is half of half. which is like that of manganese 3 gallium carbon. And the EXAFS also shows the same thing, that there are clusters which are rich in gallium and there are clusters which are rich in tin. And we say therefore that in the gallium rich regions, the ordering is as per half of half, and in the tin rich regions, it is as per half of 0.
Oh yeah, microscopically it's understandable, but the macroscopic magnetic property is somewhat different from the
macroscopically, if I can just go up, yes. So this is the magnetization. So this feature is at around 155 Kelvin. Okay, so this is the where you see a sudden decrease in the magnetization and then an increase. So that is the ordering, magnetic ordering temperature.
I see. Okay, interesting. Thank you.
So, any other questions, comments? So, can I have one question?
Yeah.
Yes.
So, this same topic.
Yes.
So, have you tried to carry out the transmission electron microscope or the microscopic technique?
We have done SEM, scanning electron, but we do not have good access to transmission electron microscope. So we have not done that. Yes, we will do.
Maybe we can do some microscopic method.
Yes.
We will have some cluster size and
we will definitely. I will definitely,
more information and that ordering, or I don't know, but very interesting. Yeah,
we will do that. We will definitely do it.
Thank you very much. So, another question, comments?
Yeah.
Okay,
if
please.
I can ask one. Hello, Professor Priolkar. Nice to see you again after a long time, and fantastic talk. Wonderful results. So I had a quick question on slide number 39. Maybe I misunderstood something. If you go to slide number 39, and when you show the lattice constant, so there is a discontinuity, I notice.
No, that is that. Sorry, it's not a discontinuity.
Okay,
in
so
order
because,
to,
sure,
I have actually put a break in the.
Yes. So now I can see that clearly, because I thought I saw somewhere it follows perfectly Wegener's law, and then I suddenly missed it. Okay, so that is clear now. And the second question is, when you're talking about the linear combination fit with clusters, do you have any estimate of the cluster size?
No, we have not estimated these cluster size from EXAFS or structural probes. But if we try to look at whether these are super paramagnets or spin glass, or in that sort of from the magnetic probe, so they will be large enough clusters, but we have not estimated the actual sizes of this.
Right, but they would be typically much smaller length scales than what diffraction is seeing, but then EXAFS can catch that. So maybe it's order of few angstroms and not really,
possible.
Fantastic. Thank you so much.
Yes,
thank you. So, any other questions? No more. Okay, thank you very much, Professor Priolkar.